Hello everyone, I am Dattatreya Nikam. Welcome you all on our channel eFunda for new day, new topic. And our today's topic is understanding of a logic diagram, part 12M1. This is a continuation series of our part 12 where instrumentation deliverables are covered. This topic is related to control system engineering where the implementation of a logic diagram is being covered. And if you are new to our channel, then please visit to our channel eFunda and watch all the videos created related to the various topics of engineering which can separately publish on our channel eFunda. And if you are new to our channel, then don't forget to subscribe to our channel and press bell icon to get the latest notification on upload of our new video on our channel eFunda. Also, eFunda team has created a membership option. You have to just click on a join button and understand the various types of a membership by which you can get lot of benefits. So let's begin with our today's topic, that is understanding of a logic diagram part 12M1. Understanding on a logic diagram. A logic diagram is a graphical tool used to represent how a control system or a safety system responds to specific inputs like sensor switches to produce output like alarm, trips, or a motor start. One can refer to the picture where the different type of logical sequence are being represented, and it is essential in instrumentation, automation, and electrical systems for designing, troubleshooting, and understanding the control logic. It comes with a purpose of a logic diagram. First, define the logical relationship between the process condition and a control action. Second, show how inputs are being combined with the help of logic gates and or not. This is depends on which type of a logical sequence you are going to prepare to deliver controlled output. Third, use in PLC DCS programming, safety shutdown systems, and automation logic. The common usages are: first, process interlocks; second, emergency shutdowns, that is ESD; auto start stop sequence; alarm and a trip logic. The last one is a PLC and a DCS control system. This is how the understanding should be clear, the purpose of the logic diagram and their common use to achieve the mentioned task as part of the control system design. Moving on to understanding of a types of a logic. Here we will see the comparison between various types of logics. We will see type, description, and common use of those logic diagram. First, Boolean logic diagram. Description uses basic logic gates and, or, not, NAND, NOR, etc., and commonly used for trip logic, interlock, and control permissive. Second, relay logic diagram, that is RLD. Description: electrical ladder type diagram showing hardwired relay and a contactor logic, mainly used for motor control circuit, MCC panel wiring. Third, ISA binary logic diagram. Description: developed using ISA 5.2 standard symbols to represent control logic and commonly used for ESD, fire and gas, shutdown logic, etc. Fourth, SAMA logic diagram, functional block based logic and used to describe analog control loop, example PID, filter, summing junction, etc. Used for detailed process control, especially in a power plant. Fifth, sequential function chart, that is SFC. Description is for graphical programming method showing step-by-step sequence, commonly used for batch processes, sequential machine operation. Sixth, functional block diagram, that is FBD, visual programming method used in PLC and DCS, uses function blocks connected by signal under description and commonly used for advanced control strategies in automation system. Seventh, a ladder logic diagram. Traditional relay-based graphical programming language for PLC, commonly used for industrial automation, basic control system, etc. 8. State transition diagram represent different states and a transition triggered by event is used for the description, commonly used for mode switching, sequence control and HMI state logic. 9. Cause and effect matrix, that is a CE. Tabular logic diagram shows input, that is a causes, and resulting output is a effect, commonly used for a safety system, FNG and ESD and trip scenarios. 10th, a timing diagram. It illustrates the behavior of a signals over time, the inputs and outputs, and commonly used for validating logic operation with a time delay or sequences. This is how we have tried to cover different types of a logic diagram are being used in the industry. The various applications may change the type of a logic diagram and its implementation. In this video, we will try to understand more about the logic diagram. It is very important to understand control logic, a quick reference, that is type, application and a format. We will see the tabulated format to cover the logic type, a digital and analog signal type, using and a format type. First, Boolean logic, that is a digital type used for interlock and shutdown purpose. Format are gates. Relay logic, digital, hardwire panel and a ladder type format. ISA logic, digital, used for ESD FNG format, ISA 5.2 symbols. SAMA, analog type, used for process control, format is a function block. SFC, that is a digital type, used in a batch control, format is a step chart. FBD, that is a both analog and a digital, used for PLC and a DCS. Format is a block diagram type. Ladder logic, it's a digital type used for PLC programming, and format is a rung type. State diagram, it's a digital type and then used in mode handling. Format is a states or transitions. Cause and effect matrix are digital, used for safety systems, and format is a tabulated type method. Timing diagram is digital, used in time-based validation purpose, and format is a waveform to indicate the transition time from 0 to 1 and to include the timing delay based on the application. After seeing quick reference related to the logic diagram, now moving on to basic element and their function in a logic diagram, we will see the detail element symbol for those item which are being used as a element, then the function of element and the example how it is being implemented. We'll see one by one. First, initiator, that is input symbol, example LSHH dash 101 is the tag number. Function, field device that starts the logic switch or a sensor type, example level switch becomes high high. Second, logic gates, symbol and or not. Function, combine multiple signals, example trip pump if both pressure and temperature are high. Third, a timer, there is a T on and T off. Function, delay logic action by time, example delay fan start for 10 second. Latch, symbol memory element. Function, maintains output even after input resets, example ESD latch until manual reset is being implemented. Output, that is actuator, symbol XV101 P-101. Function, final control element, valve and a motor, example start pump, close valve. Manual control, that is a push button. Selector switch is the symbol being used. Function, operator inputs, that is a operator intervention. An example, manual override or a reset system. This is how these are the basic elements and their functionality. It is very important and that will help you to understand logic correctly and their implementation based on the process conditions given for safety related systems. Now, the most commonly used types and a key difference between ISA versus SAMA logic. ISA logic and a SAMA logic diagram, which are both used in a control system design but serves a different purpose and follow different conventions. We will see the difference with respect to aspect ISA logic diagram and SAMA logic. We will see one by one. First is the full name. ISA is the International Society of Automation, whereas the SAMA logic is the Scientific Apparatus Makers Association. Purpose: ISA logic to represent control interlocks, logic and safety sequences, especially in instrumentation systems. SAMA logic to provide detailed functional description of a control systems, mainly in the process industries like power and utilities. Focus: under ISA, control and safety logic, that is a trip, shutdown, interlocks are being used and a focus is given. Whereas a SAMA logic, a detailed control strategy, that is a loop, feedback and a feed forward type control. Application: ISA logic widely used in oil and gas, petrochemical and a modular plant, whereas the SAMA logic mostly used in a power plant, utility control system. Complexity: ISA logic are simpler, mainly logic gates, that is and or not, timer, relay, etc. Whereas SAMA logic are more complex, which include functional blocks like PID, lead lag, bias, filter, and many others. Applicable standards: ISA based on ISA 5.2 binary logic diagram, whereas SAMA logic is based on SAMA PMC 22.1 standard. Representation style: ISA logic is a symbolic logic gate based, whereas a SAMA logic is a functional block based. Detail control behavior type style representation is being used. Use of a function block: ISA logic limited, that is on off valve or on off logic, latch, timer, etc. Whereas the SAMA logic is a extensive use of a functional block like PID, summing, comparator, selector, etc. Readability: ISA logic is easier for technicians and maintenance, whereas the SAMA logic are more suitable for control engineers and a system designer. Output elements: ISA logic typically based on the relay contact, alarm and shutdowns, whereas the SAMA logic output of a control loops, that is analog signal, set point, etc. Used in a PLC DCS programming. ISA logic are suitable for a DCS PLC logic diagram, especially for ESD and FNG type application, whereas the SAMA logic translated to the detailed DCS control configuration. This is how we try to differentiate between ISA logic diagram and a SAMA logic diagram. You need to study this and then you need to implement based on your project scope requirement, and maybe this video will help you to understand logic diagram and their applications. Now we will see example comparison of ISA versus SAMA logic. First is the ISA logic diagram, that is a simple interlock. One can refer the typical interlock where the gates are shown but the correct and exact symbols are not used. So as to make the simplified version for this video, LSHH101 and LSHH102 are given to the OR gate, and based on the action or initiator action, trip command is being initiated to close XV101, and simultaneously the alarm will be given to the control system. Shows discrete logic for tripping a wall based on high level switches. focus on a binary outcome, that is a trip or a control type. This is the simplified interlock system. Sama logic diagram, that is a control loop. One can refer to the picture where the functional block details like a PV value then goes to the lead lag, then PNID controller, then limiter, then output bias, then valve position, and to operate this lead lag network will take the set points for comparison of a PV and a set point value. This is how the control loop is being operated. Describes full analog control behavior, include a dynamic response, tuning blocks, and modifier. Also useful for understanding loop stability and responses. Now we will see the simplified version for better understanding when to use. One can refer to the table where the scenario, use of a ISA logic and use of a SAMA are shown. First, ESD or FNG system use ISA logic. Interlocks for motor and valve use ISA logic. A detailed analog control loop example, boiler drum level use SAMA logic type. DCS function block diagram use SAMA logic. Technician level troubleshooting use ISA logic. Control algorithm design in power plant use SAMA logic. This is how we have differentiated more in detail with the help of example. Now we have reached to the stage where input document and function implementation is to be understand. It is very important to understand the input requirement and their functionality implementation, as we will see in a brief. Input document requirement. First, PNID, that is a piping and instrumentation diagram. To understand the instrument location and a tag number, control function, type of a devices, that is a switch, a transmitter, control valve, and a valve fail safe action. Second, cause and effect diagram provides a initiator, that is input, sensor, push button, ESDs, and a B is effect, that is output, alarms, trips, valve closures. Third, timer delay in a logic diagram. The purpose is a delay activation and a deactivation of output. B, avoid nuisance trip from transient signal and a sequence operation in a controlled manner. Fourth, manual override function. This allows operator to A, override automatic trips or starts, B, reset the function manually, and C, bypass condition only if safe. Fifth is the additional consideration for a logic development. Now one can refer to the table where element and descriptions are shown. Timer, that is a T on T off, delay action after condition is true. Latching keeps the output active even if initiator reset. Reset logic, manual or auto reset after trip. Voting logic used in FNG system, 1 out of 2 or 2 out of 3. Fail safe design, that is ensure safety in power failure condition. This is how today we have tried to cover the topic of understanding of a logic diagram, and hope this video will help you to understand the logic diagram importance and their implementation. Further in next video we will see how the logics are being implemented with the help of few examples and a more detailed study of a logic diagram.